Good afternoon. For the announcement first, the next Research Exchange I4 Energy Seminar is on December 4th, and it'll be Mike Isaacson from UC Santa Cruz on community renewable energy. I don't think I got the title exactly right, but that's the substance of it. Today's my pleasure to introduce Ann Piette, who is a Berkeley grad, and
Go Bears.
And let me call her a denizen of Berkeley for many, many years at the leading department at Lawrence Berkeley National Laboratory as of about 2 years ago. And she is an expert on building science and on many aspects of building science. But in particular, she's been responsible for developing technology for automation in demand response. And she'll tell you more about that. But there's some exciting developments in that field, in particular as they relate to the integration of variable supply sources, renewable energy, so that we're finding a situation which, as the title indicates on the talk, demand response is used to be almost exclusively event-driven. That is, some crisis when you needed to find new supply from the demand side, to something that we're thinking about doing all the time. Marianne?
Thank you. So it's a pleasure to be here today. I want to thank Citrus and Carl for inviting me and introducing me. I've had the pleasure of working with Carl for 30 years now this year. When I was in Art Rosenfeld's Physics 180 class at UC Berkeley, we developed a backdraft damper for Latimer Hall because of some fan and energy waste going on there. So I've worked with Carl for 3 decades now. And a lot of our work on monitoring-based commissioning was funded by CIEE. And some of the work in demand response comes from our ability to understand the status of commercial building control systems, how well they work, and what the culture is for facilities. I'm from Lawrence Berkeley National Lab up the hill, and I'm going to talk to you primarily about demand response, but I wanted to first give you a quick introduction into the way we're organized around grid integration. This is not my department. My department is just this little bit down here, but we have work in batteries, we have work in computational systems. I'll be talking mostly about this area in demand response. We also have an electricity markets and policy group, and we benefited in our technology work from having a collaboration with that group. That group works with regulators and the economics of the grid. Today I'm going to be talking about the motivation for something called Open Automated Demand Response, OpenADR, and I'll introduce you to what it is, and I'll talk about what the status of it, and I'm happy to say over 1,300 facilities in California currently have it installed. I'll talk a little about that, but we know for all the utilities and several of the munis are supporting it. And then we'll talk about the future. How many of you have heard of the duck curve? Oh, wow. You guys know about the duck curve, so you've spoiled the fun part of the talk, because when this technology was developed, we were concerned about the hot summer days. And the Ron Hoffman, who's not here today, many of you know, this is actually Ron's idea, this work. And we benefited from a decade of collaboration with CIEE and with Ron, also Roger Levy, who's not here, and Roger helped us navigate the Public Utilities Commission. But the concept was, we had an electricity crisis about 10 years ago. We were very concerned. At that time, the peak was growing faster than the base load. So we had a lot of growth in the inland areas in California. We had a lot of growth in Stockton and Tracy and Palm Springs. And California was very concerned about that growth, because those high-priced days, it's really remarkable that going from 45 gigawatts to 50 gigawatts was less than 1% of the hours. So the whole system has to be bigger. It has to be more power plants, more transmission, more distribution, more expensive. So the theory was, and Severin Bornstein here from UC Berkeley was a founding participant in the theory that if we move the state towards default dynamic pricing, we would reduce the number of hours we were up here, and we would reduce the likelihood of blackouts and brownouts. Now, our blackouts and brownouts were not on hot summer days. They were market design issues. So there's this challenge between what's happening in the grid and what's happening in the markets. But the concept was we wanted to reduce this peak by automating the dynamic price response. And I'll tell you as we go a little about how that's played out. So the concept was we wanted to develop automation systems that were low cost that would allow us to get signals to buildings. And then once we got a signal to a building, what could the building do? So that was our research question. We developed something called OpenADR, which I'm going to talk about, and it's used in utility and ISO programs. It's used in more than 8 countries around the world now. Rish Gottakar, one of our standards guys, was in Switzerland this past week working on the IEC standard. So we've made a lot of progress starting here in Berkeley with Ron Hoffman's idea. This is a graphic to show you the basic characteristics of OpenADR. It is a client-server system. It is an open API. When we use the word open, we're referring to an open API. We did have OpenADR 1.0 and 2.0, and I'll talk about the differences there. And we did have open source toolkits at one point, but OpenADR is not open source. There are open source tools, and Enernoc, one of the biggest aggregators, has an open source toolkit for OpenADR 2.0. And I'll talk about 2.0. But basically, it is an open API, and it was an open process. So when we first started doing it in 2002 is when we first had the idea. 2003 is when we did the first field tests. The idea is you take the electricity prices and you represent them in an OpenADR data model. So it's an application layer model. We are using the internet, but we could use other physical communication platforms. We've done this over FM broadcasts. We've even thought about OpenADR over AMI, OpenADR skinny, we call it. But today, most of it is done over the internet. It's a client-server architecture, so every minute of the year, over 1,300 facilities in California are continuously listening to signals from utilities. OpenADR 1.0 had API between the ISO and the automation server, as well as between the facility and the automation server. Today, OpenADR 2.0 is only this piece here, and this piece is, there are about 8 companies that make servers, and there are over 100 that make clients. So we're not standardizing this part anymore, and some utilities offer they manage their DR automation servers manually. They'll go to those and they'll call events, and others have them more integrated with their back office systems. And so that's a whole other discussion about utility back office platforms. But essentially, that's what it is. Then the building is pre-programmed to do something once those signals come in. And these signals are modes and integers, and it's a language of signals that are applied to demand response programs. So that's what essentially OpenADR is. It's this data model to allow communication and standardization of demand response. This curve is one that we use when we talk with people about how to think about demand response versus energy efficiency. To the left here is the concept that the definition of energy efficiency means you're getting the most services out of a kilowatt hour. In many cases, we don't measure the services. So it's very difficult to actually understand when we change the services for demand response, what we're actually changing. So when we reset a zone temperature, when we reset a cooling load, the tons of cooling are being reduced, but we actually often don't measure those actual tons. We are changing the service in the zone. And how much kW we get for that is highly variable. But the definition of energy efficiency means you're getting the most service out of every kilowatt hour. And those are on different time scales. As we move to the right, we care not just about how much energy you're using, but when you're using it. So the time domain of electricity use is now very important. And many years, buildings have had time of use rates. Small commercial in California is now on time of use. This will get to your homes. And small commercial in PG&E territory is going to critical peak pricing next year. So the technology, the tariffs that we have are starting to use this automation. There are many buildings that get these demand response signals day-ahead dynamic pricing without automation. The majority of demand response today is not automated. But we're moving towards a time, as you move to the right, you have to automate if you're doing it quickly. And that's where we've created a technology suite that allows us to automate DR on different timescales. And we took an IKEA that was on day-ahead hourly pricing, and we put it on a 10-minute ahead non-spin ancillary services program with the same HVAC strategy, a little bit of a different OpenADR configuration, which I'll talk about. So we essentially changed service levels for demand response. Now, this graph needs to be updated to reflect the concept of taking energy. It's not a very good graph on the concept of charging. So we can charge thermal mass, and any load that has inherent storage is the load we're interested in, better actuating. We always have known that the ability to integrate a load with a demand response signal is related to the controls. So the more granular the controls are, the easier it is to do. So newer buildings are easier than older buildings. And the speed of telemetry changes. When we do the really fast stuff, we have 4-second data on the loads. So that's the basic idea of the time scale of what we're doing. Now, in many buildings, we have ended up resetting the zone temperature on hot summer afternoons, and the people say, wow, it's more comfortable because the buildings, many are overcooled. And if you talk to the folks at the Center for the Built Environment, they will tell you that American buildings are colder in the summer and warmer in the winter, and that's the problem here. So we're overcooling, and we know there's a lot of DR. So sometimes we say, let's set up the zone temperature in the afternoon, and they'll say, oh, let's do that every day. And we say, great. Always give it to efficiency. Never false load, a low or keep it high just to dispatch it. But that becomes part of the dialogue as we move towards a future where we care a lot about renewables integration. The hot summer peak day DR and the anytime DR have a little bit of a different calculus, and we're trying to understand the benefits and valuation frameworks associated with those, which are emerging and evolving as California, that has energy efficiency and demand response at the top of the loading order, followed by distributed generation. California is very concerned about having a green out, like they're saying Germany's having. So that's the duck curve, and we'll get to that. When we first did this in 2000, our first tests were in 2003, and our first tests were a Bank of America in Concord, a library at UC Santa Barbara, Roche Pharmaceuticals in Palo Alto, an Albertsons with Enlighted, and GSA building in San Francisco. They were all different. They'd all shed load before, but it wasn't automated, so we got them a signal. In 2006, we had all of these buildings, and we had an IKEA, we had Walmart, we had Target, we had office buildings, we had some labs, data centers. Most of them reset the zone temperature. So the graph here is the strategy they chose. We didn't choose it for them. They chose a strategy. We got them the signal, and we've done a lot of work on studying what people do. And this one did lighting. A dimming ballast is one of the best examples of a technology that has that granular control for daylight dimming and energy efficiency as well as DR. So technologies that are granular offer a good DR. This one here was our first bakery. It's Svenhard's. They make those bakery in Oakland. They bought extra pans and they turned off the dishwasher. So we don't tell them what to do, but we study what they do. Up here, the blue is how they normally operate, and this one is at 76 degrees, and this one's at 70. When we went to the state and said, let's do this in all the state buildings, they said, oh, well, we do DR every day. I said, well, that's not DR. So they were running warmer, and they still are running warmer. And I was just down at UC Irvine talking about in the San Onofre region, what are they going to do? And they are running warmer. So there's less they can do. Because that energy efficiency we're talking about, they're developing fewer tons per square foot of cooling. These ones here could go 8 degrees. And that's what they decided to do. We had one site that had Hawaiian shirt day and served iced tea. So what they do in their building is a little bit of an art and a science, and the facility managers around the state are getting used to this. Not all of them are even willing to do it. And then this is what a shed looks like. This is a 100-degree day. The red is the baseline. The blue is the shed. This was a 6-hour critical peak pricing event. California's CPP price that PG&E has is now over $1 a kilowatt hour during 4 hours, so they've reduced it. And we reset the zone temperature twice, just like these little bits up here. So some of them were 2-stage resets. This is a moderate price and a high price period. So these are what sheds look like. When we aggregate them, it looks like this. So this is 20 buildings that have automated the critical peak price response, and this is a 6-hour event. We're very careful not to get a rebound, so we work carefully with the building facility managers. They either go into nighttime mode, reset the zone temperature slowly, reset the VFD slowly. So we're explicitly doing that. Up here is a 10 megawatt reduction. This is a large compressed air site that got a lot of incentives from PG&E, and they didn't turn the load back on until the next morning. This one here is cold winter mornings in Seattle. So that was our first non-hot summer day activity where we said we had a target, Seattle University, Seattle Municipal Tower. So we had campus, offices, and retail, and they have electric heat and some lighting. So they did some resets here. Going back for a moment, we do have a lot of sites that have pre-cooled, and we have studied pre-cooling. We have a lot of simulation tools, Energy Plus based, where we actually try to model the mass. So we do work in trying to use pre-cooling. It's harder to predict, and if you have a building like this, it might be pretty good. A lot of glass is not good. A library would be great. So in the mid-2000s, we began working with the Public Utilities Commission to require the utilities to work with us. And we were very fortunate. We went there almost every quarter and updated them on what we were doing. And so the state had this policy goal of moving towards dynamic pricing, and we had a technology that we wanted to test. And the PG&E was an excellent partner, working through the Emerging Technologies Program, actually, John Livingston's program at the time, where we actually got ET funding to test this in some buildings. And then we were very fortunate in 2009, we published the spec. So the spec was written down, all the utilities had tested it. That was the same time when the NIST Smart Grid standards were starting. So we gave the entire spec to something called OASIS, which is the Organization for Advancement of Structured Information Systems. That's a standards development organization, a NIST SDO, and OpenADR 2.0 is out now, and that's a national standard that was developed through a consensus process. It's got some differences. It is not backward compatible. We have what's called OpenADR 2.0A and 2.0B. 2.0A is our simpler client, and 2.0B is a more robust data exchange platform. And we have over 100 members in the OpenADR Alliance now. Johnson, Honeywell, Siemens, Schneider, Google recently joined, PG&E, and that's been very successful in creating the certification and testing. So now when you buy an OpenADR client from in your automated logic control system, it's a conforming client that's been tested. So utilities can now say they're going to spec 2.0B, they'll get a server that can talk with anyone's client. And that is the power of what we've done. It is now, I was talking to SMUD yesterday, excuse me, and when they go to a Lutron or Philips and say, we want a lighting controller with OpenADR, that exists. So 10 years later, we've actually created something that's been commercialized. The 2.0 is quite new still, but it is seeing a good market uptake, and we're excited about the next generation of technology. The U.S. Green Buildings Council is trying to require DR points in the LEED program, and we're working with them on that. And one thing that's not up here is Title 24. There's now a requirement in Title 24 that a building has to be able to receive automated DR signals, and we're going to be working with the utilities to educate them. If you're a building owner and you have a building over 10,000 square feet, your lighting and your HVAC systems have to be able to receive an automated DR signal. We're not the only signal in town. There's something called multi-speak, which is used by a lot of rural co-ops. And there's Smart Energy Profile, which some of you know, which is the meter communications that AMI initially had SEP1, and SEP2 is just coming out, and that's actually an IP stack, so it doesn't require the advanced meters. That's a long story in itself I'd be happy to talk about, but OpenADR is very successful in creating a commercial standardized signaling system for demand response. This is what the current numbers look like for SoCal Edison and for PG&E. Internoc and Energy Connect and the large aggregators support OpenADR now also. So we've been able to get them to try this out and realize it's not that hard to do. So we have, this does not include the San Diego or the SMUD sites. And this is about 1,000, let's see the numbers right here. 740 and 300. So we're a bit over 1,000 in these numbers here. You can see there's what are called direct enrollment and aggregator, and then some are both. So we can actually be on critical peak pricing and be on an aggregator program as well. So you can see the number of megawatts. We have this is about 220. In California, we're estimating about 260 megawatts, or about a quarter of a gigawatt, are using the standard now. Now, those are all in different kinds of programs. They're in capacity bidding, critical peak pricing, most of the hot summer DR. Okay, and as we transition to the anytime DR, we'll start talking about that. I wanted to show you this one. This is a project in New York City. This is a project where we have these three buildings: the Metropolitan Transportation Authority, One World Financial Center, Paramount, and NYU. These buildings they have peak demand charges, day-ahead hourly pricing, and emergency DR events. And we've modeled the price of the owner's bill to try to minimize their bill and automate signals using an Energy Plus model to predict what are the control strategies for them to change their load shape. So this one is more, it's a more price response model that is multi-platform, multi-program integration. And that's important because the DR programs that the utilities currently offer are price-based programs, many of them, or events, but they're not integrated with the rates, the demand charges, and the time of use charges. So we need to really, the customers want to minimize their bill. And this is a technique to try to start doing some of that. Now, this is the duck curve. You've seen it before. What's interesting about the duck curve is this is a springtime day. Okay, we're still going to have those hot summer peaks, but what we care about now is what's happening late in the afternoon when the solar comes off the load shape and loads are peaking now 6, 7, 8 p.m. I saw some data from SMUD yesterday where they had some commercial buildings with PV on site, NDR, and they see shapes like this. So this is a different time of day than the traditional 2, 3, 4 p.m. DR. And this ramp time could change over the year. So it's a big concern in California is how the ISO is going to manage the grid when we have more renewables on the grid. And the concept is, can demand be flexible? And we know on hot summer days, we have some ideas of what to do. What can we do other times of the year? So that's been a subject of a lot of our work recently. This is the first project that we did with PG&E to say, we were asked, how can demand response look like a Gridscale battery? And the question here was, I'm going to talk about this architecture for a moment. So the concept here was, the ISO has these AGC signals that's going to the automation server, and the same client that was using for critical peak pricing is now getting a much faster signal and a real-time KW. When I haven't said this yet, but when we send prices to the building and the building's pre-programmed to do something, we don't have real-time KW. They'll see it next day, but there's not a feedback loop. This one has a feedback loop. So we're actually trying to get a particular shape that we're bidding into the wholesale markets. And the DR strategy will be more or less aggressive to hit a certain kW. So it's a simple feedback loop, but what we wanted to understand was the latency of the communications. This technology uses a push signal rather than a pull. When we're behind the firewall in a lot of sites, the client goes and finds the server and gets the price every minute. But in this architecture, we're using a faster internet dedicated signal that pushes the DR signal to the client much quicker. So we got round trip in less than a minute, and the communication had to be able to get the signal and get the kW back to the ISO to make these faster loads respond. So this is an example of an activity that we're doing a fair amount of work on. We have a study with the other national labs, with Oak Ridge and NREL, and this has just been published. It's the number one, it's the top of our pubs list at drrc.lbl.gov if you go to our pubs list. And here, we're looking at all loads. This is a bottom-up study of the western region. So this is WEC. And the question was, what loads are available in the middle of winter, in the middle of the night? What loads are available on the spring morning? And we developed a model of loads. These are loads that have all participated in demand response programs before. And the research agenda here was to consider the speed of the response. Is it controllable? Does it have a rebound? Is it predictable? The predictable is important. We took our most predictable office buildings and retail buildings and put them into these non-spin ISO programs. So here, we wanted to make sure that we developed a framework to evaluate what loads might be candidates for this anytime DR. So this is a paper study. This is what some of the data look like. So this is for the entire western region. And these are ranges. So we're getting into the gigawatts of response for these different regulation, flexibility, contingency, energy shift, and capacity. These data are fed into Plexus models. NREL is developing and Livermore is developing. And we're modeling demand response on the grid continuously. This is not economic price points. This is technical capability. So this one says ag pumping, commercial lighting, commercial ventilation, commercial cooling, residential cooling. So we've created these maps of potentials for demand response resources to characterize what we think might be available on the electric grid that exists today. This is a project that I want to mention that's pretty exciting. There's a lot of concern about vehicle to grid, and as we have more electric batteries on the distribution circuits, there's a lot of question about charging. This project is about actually getting this is a fleet of 40 vehicles, and the vehicles are scheduled. So if you're at the LA Air Force Base and you want to drive tomorrow, you check that car out. If that car is not checked out, that battery is available to a scheduling coordinator to send a regulation bid to the ISO. So this is the development of the architecture, which uses a distributed, this is a microgrid optimization model, the e-mobility fleet management system, the OpenADR automation server, the scheduling coordinator, which SoCal Edison is participating in, to the ISO for these regulation services. So this is a complex system, but the DoD is actually very interested in these systems because what it does is it allows these vehicles to be monetized through new services. And it's a question, to do this with an individual car is going to be a lot harder than with a fleet. This is some work from Stephen Lanzasera, some of you know. This is an ARPA-E project that we have with a company called AutoGrid. AutoGrid is developing technology to try to take the historic DR performance of a load and dispatch it for a utility portfolio of demand response programs to allow the load to have the most value in the DR portfolio. There's a lot of companies doing things like that. It's difficult to do because these DR programs are still emerging. This technology, you can see we're using SMAP that some of you know about. We're actually developing low-cost telemetry platforms that we think residential loads might be able to be aggregated for some of these ancillary services. So the question is, how low can we go? How cheap can we make the DR automation and telemetry platform that the ISO sees the load? So here, our target is less than $75 a kilowatt. I forgot the per kilowatt there. And we're looking at pool pumps, air conditioners, continuous ventilation in homes. We'll be looking at a variety of different loads that can be continuously dispatched. A pool pump, we know, is a good one because over 24 hours it needs to run so many hours. But what hours those are can be flexible. So any load that has that kind of a flexibility, we want to understand, can we get a control platform to communicate with it? Oh, I did. This is a related project Stephen's working on with us, and the Pacific Northwest National Lab has developed something called Voltron, which is a message bus autonomous agent platform. Okay, so this is a DOE-funded effort for DOE's investment in transactive controls. The concept of transactive controls goes beyond the traditional demand response vision, and that they believe that you could transact with your neighborhood. It's not today's market because you can't sell electricity to your neighbor. That's not allowed. There may be a day when it is, but you'd have to settle. You have to measure. You have to have settlement grade measurement if you're going to sell electricity to your neighbor. So there could be a lot of shysters out there with meters that aren't properly calibrated selling electricity to their neighbors. Or can my neighbor charge his EV on my solar system? Because my solar system's selling extra capacity. So that's the vision. The vision is well ahead of the regulatory markets we have today. We've been developing a continuous M&V monitoring and verification baselines that look at cumulative energy savings and DR events. Pacific Northwest Lab has built this Voltron light. This is an open source platform that will be available soon. And many of the aggregators are interested. We're developing some lighting agents to go with this platform. And it's essentially a message bus for autonomous agents to control buildings, and eventually for the buildings to communicate to the grid. Now I'm going to talk a little about FlexLab. And up at Lawrence Berkeley National Lab, we have a new facility that is allowing us to design experiments to model, control, and measure buildings like we've never been able to do before. This is a 9,000 square feet of test beds. I'm going to show you a video about this one here. These test beds are side-by-side test beds. So they're designed to let us run one test bed one way, run the other one another way, and configure them to run as a whole buildings with HVAC, lighting, plug loads, facade controls, and to think about modes of control that we don't have in buildings today. So we have these exterior test beds, which are these ones here. We have a 1980s vintage, a 2013 vintage, and a net zero ready vintage. So we're building them with different systems so they represent the building stock. And they're going to be used for code and building code analysis, validating model predictive control systems, which I'm going to talk about in a moment, and also doing some work in visualization. We are in the process. I'm going to talk to you a moment about something called Modelica. Because of this anytime DR, we're starting to see the modes of building operation to go beyond the historical footprint of a building end-use services. There's a lot of interest in putting batteries behind the meter. There's a lot of new interest in thermal storage. And there's a lot of interest in what loads are flexible. So we now have a desire for models as part of the building control system that we didn't have before. I call them energy-aware controls. In the past, you pay the bill once a month and you run the building. But we're now at this time where the building is being asked to do new things, and we really need models of the end uses and those services to understand the modes of control and how to run the building as a system. So we're going to be calibrating this test bed in the next year, doing the baseline modeling, and I'll talk about Modelica in a moment, and then this use case validation. I'll talk a little about the capabilities of this technology. The test beds have very detailed measurement systems built in. We have 3 different levels of concrete. We have both radiative heating and cooling in the floors. We have air and hydronic zonal systems. We have dynamic facades. We have daylighting and a variety of lighting and plug load systems we're testing. So we're very interested in improving the measurement and modeling in real time to allow us to do different control scenarios and allowing manufacturers to bring their technology in and test them. So Honeywell and Johnson's and Siemens and stuff are very interested in accessing the facility to explore these new control strategies. And what would you do if you had an electric battery as part of the control system? How would you use that battery? This is an example of what we do with Modelica. Modelica is an object-oriented language that is the future of modeling in buildings. Energy Plus has been around. Well, we had DO2, then Energy Plus. Energy Plus is a whole building model. Modelica is an object-oriented library for control system objects. So you start by taking some sort of design and developing a feedback control system to model the plant, and then you do a hardware-in-the-loop test, and you can then test it in the actual facility at scale and quantify the annual benefits of these new platforms. So the Modelica Library is where we're moving towards, where we would actually have a set of equations and solvers to model the control system that we can't do with our simulation models today. So this is an open source toolkit that's we're doing the collaboration funded by DOE, collaborating with the Europeans, and then developing methods to bring advanced control systems into commercial buildings. So this is my last slide, but then I have a video I'm going to show you really quickly. I want to make 4 points here. I've talked a little about the need to understand the demand-side loads and their ability to respond to the grid at different time scales. That is a really important thing because people are working on refrigerators, they're working on water heaters, they're working on data centers. We want to understand what loads exist today and how to get them to respond to the grid. Standard communication systems show promise for low-cost automation. This OpenADR 2.0, I didn't say it, but we've been retrofitting with gateway boxes that have that communication system. The idea is to embed it in smaller and smaller systems. So we can communicate with ballast, we can communicate with, and what that design looks like, is it at a central system in the building or is it distributed intelligence? There's a lot of challenges there on the architecture for these communicating systems. Model predictive control is needed for these energy-aware automation. We know we have to have real-time KW. That matters for energy efficiency, for demand response, for grid integration, and I didn't mention the volt-var control. So conservation voltage reduction is coming, and we need to understand the loads in the building and the power factor issues associated with the loads as well. And then finally, new opportunities to link demand response and energy efficiency and distributed generation. I didn't talk a lot about that explicitly, but the concept is when you have a PV system, you may control the building differently than you have historically. And we're very early in our understanding of buildings that actually are more responsive to these outside systems. Historically, the building runs, you pay the bill once a month, and nobody knows what it's doing. But we're coming to a time where we can do much more, and the building can pre-cool, it can change the facades, it can change the light level, and it can participate in the grid to try to help reduce the need to help manage the variability from the generators. And when the wind is blowing, it's storing, and when the ramp is coming, it's shedding. So the signals from the ISO are evolving, and we're trying to get the buildings to be responsive. So this last thing I'm going to show you is the FlexLab video. And I think So this is an animation of what FlexLab, some features of FlexLab. These are the side-by-side test beds. And you're going to see a variety of the architectural elements to give you an idea of the modes of modes of control and the kinds of things that we can do with the building. We have adiabatic walls between the spaces, and they can be taken out into one big cell, or they can be smaller cells, and we can even put partitions in there for different office spaces. As I mentioned, there's both air and water to the zone, as well as in the floor, we'll have radiant heating and cooling in the slab. So we can do pre-cooling. We could do an underfloor air system, the UFAD systems that the Center for Built Environment's very good at as well. Those we could retrofit them in. You're going to see a number of windows. The windows influence the conduction, the convection, and the radiation. You're going to get differences in the solar controls. You're going to get shading. So a lot of differences in shading. There's a lot of work in automated shading so that we managed to glare. We had Google's very interested in using FlexLab to help develop their new offices. Genentech is developing a set of new offices by using FlexLab to mock up spaces. We have two double-skin facades, like some of the German double airflow windows. We will not have the photovoltaics, but we will have an idea of how big of an array would it be needed to power something like FlexLab. We will not have the green roofs, but it could be retrofitted with something like that. We will have the capability to do this next feature, which is the skylights. The skylights obviously allow us to reduce the electric lights and manage the thermal and the radiative issues associated with the skylights. And then finally, this test cell is very unique worldwide in that it actually rotates. So it allows us to change the sun angle and the prevailing wind to test natural ventilation. And the folks in Singapore are building one of these on top of one of their buildings. So we have a lot of collaboration with test facilities around the world, Norwegian test facility, and I'll stop there and take questions.
I believe there's a good deal of evidence that control of energy use by users of and occupants of commercial buildings contributes a lot to their happiness and productivity. But superficially, it would seem that control by users and automated control are incompatible. Is there a way to integrate them, or is that a conflict?
So I agree with you. We know people like to be able to control their space. The best example would be to be able to turn off or on a light or to dim it. And if you have a daylight dimming system, you're right that they might want their light on, but the daylight dimming system may dim it. Normally, daylight dimming systems are set for a certain foot candle level, so that if they turn on their light, if there's sufficient outdoor light, it's already dimmed. We don't see people actually turn their lights off more than they turn them on. Obviously, with seasons, they'll like to turn them on. Temperature control, I'm actually a big fan of what some of CBE does with the heated and cooled chairs and the foot warmers. The one thing I would say is task ambient systems, where the background lighting and the background conditioning is one thing, and where you are and sitting, people like to control that. So you can have both. The person's going to be they're going to control their workstation, but the background ambient conditions may be different.
In the FlexLab system, do you also measure local micro-weather, microclimate, and to see how predictable that can be? Right.
So we obviously have, look at this, it's still going, sorry about that. We obviously are a little bit constrained because we are in Berkeley and it's very mild here. So there's a couple answers to your question. One is we will primarily extend to other climates using simulations. So if we can calibrate the model for our climate and extend it to other climates with simulation. We can false load rooms by heating up one room and creating a load on the other. And the HVAC is designed so we can actually false load a humid climate sort of thing. So we have a lot of ability to create. What the people that designed this have told me is we can do a Denver climate, so we can get things as cold as Denver and as hot as Denver, but that's about it. So we can do some false loading.
Thanks. With respect to the electric service supplied by demand response, can you give some idea of the dollar flows associated with the service and which categories and who's making the money?
Right. So the majority of the hot summer programs, there's a variety of ways that customers get paid to participate in those programs. SMUD is paying the least amount, but they're making the least penalties. So normally the more you provide, there's more risk. And if you are doing it through prices and through voluntary programs, there's less risk, but you get paid less. California's dynamic price is over $1 a kilowatt hour compared to more like 15 cents on a normal day. And then you get savings other days. The prices for AutoDR, which I haven't said, we're spending $100 to $200 a kilowatt to install the technology, which the utilities are paying for. But the people are getting from like 20 cents to $1 a kilowatt hour for participating in the programs. The really fast TR, they will get more, but we don't actually need as many megawatts there, and that's one of the things that we think you may be able to supply all ancillary services from demand-side loads, which would reduce the need for these standby power plants to be producing those. But the market for those products is still evolving, and around the country, there is a report on our website that goes through the cost per megawatt and cost per megawatt hour that different ISOs are offering around the country. I don't remember the numbers off the top of my head, and I'll add some of that to this, but those numbers are, they tend to be, at the high end, $1 a kilowatt hour or $1,000 a megawatt hour.
For the system you mentioned that has the push signals and the response to the kilowatt hours, how is that related to the rest of OpenADR?
Good question. So OpenADR has a variety of types of signals, as I mentioned, and the client at the building didn't have to be changed, but the signals, well, actually I should think about it. It did have to be changed to receive those signals. OpenADR is like a language of signals, and any particular program uses them in a certain way. So the fast OpenADR, this OpenADR 2.0b, which is the new one, that has this real-time feedback, which the client that the building owner has to send the information, be able to send the information back to the utility, but the program may not use that information. So it's a very case-by-case specific implementation, and there's not a lot written yet on how utilities are actually using the signaling systems. But and be happy to. There's a lot of papers on our website that go into more details on the specific signals.
I'm curious what sort of work is being done to address potential security concerns.
Yeah.
In the communication via OpenADR
Sure.
and that multi-agent control bus that you discussed briefly.
Yeah. So OpenADR always had normal encryption and authentication, and the key exchange for configuring a client is pretty well understood. It's just like a banking, internet service, and it's a one-to-one relationship between the utility and the client. 2.0 has the same features. The Voltron technology is much newer, and I was just talking with Therese about SMAP and the need to take a close look at some of the security issues in SMAP that we think are a concern. But OpenADR had in the NIST Smart Grid standards, there's a security review process, and OpenADR went through all of it.